Yeah, so for those of you I haven't met yet, my name's Thomas Campbell. I come from St. Louis University, and I'm in Paul Brocker's lab. He's a new assistant professor, so this is kind of the first, let's say, coherent story that we have to talk about, and so I'm excited to share that with you guys. And we're interested in fundamental questions that have been around for a long, long time. Back in biblical times, Matthew was pondering, if salt loses its saltiness, how can we make it salty again? And even today, on the Today Show, we're still asking questions about salt. And thankfully, these questions have almost nothing to do with my research, but at least I got your attention, so. We are interested in salt, though, specifically salts of sodium and potassium. And the reason we're interested in these salts is because we see universal enrichment of potassium across all of modern biology. So all cells today spend a tremendous amount of energy enriching potassium and expelling sodium. And we want to understand why these selective gradients are universally conserved. We work under the assumption that something that's ubiquitous like this, developed early on, is conserved throughout evolution because it's important, and it's probably fundamental in nature, which is what leads us to prebiotic chemistry. So we want to understand, how do these ions impact reactions that are relevant to prebiotic chemistry, and we want to start with the simplest systems we can pretty much possibly imagine. So that brings us to peptides. We've talked a little bit about peptides over the past couple days. But why peptides? First, they're obvious prebiotic relevance. Second, they're relatively well understood. By that I mean we have a lot of information to go off of. They've been studied for a long time, both in the context of prebiotic chemistry and other contexts. And why hydrolysis? So this is something that Becky just touched on a little bit. Obviously, the goal is to drive condensation. That's what we need to build complexity. But these reactions are in competition, and in order to understand the more messy condensation, we first want to understand hydrolysis, because that's going to be going on in the background all the time. And again, it's simpler. We have one reactant, one product, in the case of a homodimer at least. And so I'll highlight again the emphasis on fundamental reactions. So hopefully we can just understand the basics first, and then apply what we observe to kind of messier systems down the line. Okay, that got pretty blurry, but this is just a couple notes on our methods. We're doing the hydrolysis of dipeptides. We do everything with NMR, so pretty simple. Just measure the integration of the peaks of the reactants and the products over time, get the rate constant. But what I wanted to point out is that you can't see it, but we have 1 molar HCl. That's key because the half-life of a peptide bond at neutral pH is painstakingly slow, and I want to graduate eventually. So we use an acid catalyst, and we have an excess of acid, which is important because then we observe pseudo first-order reaction kinetics, so it kind of simplifies things there a little bit also. So when we do this experiment for we did 4 dipeptides, all the possible combinations of glycine and alanine, so gly-gly, gly-ala, ala-gly, and then ala-ala. So these are the 2 most simple amino acids, the most prebiotically abundant amino acids, so they're kind of the obvious choice there. And when we measure this in the presence of sodium chloride and potassium chloride, in every case, the hydrolysis proceeds faster in the presence of sodium, and slightly slower in the presence of potassium. So this was cool. We're excited about that, and you know, it's definitely interesting, but it gets a little bit more interesting, and that's we got to talk about cyclic dimers now. So whenever we talk about peptides in the context of prebiotic chemistry, we have to also consider cyclic dimers, because this is the general reaction scheme of prebiotic long-chain polypeptide synthesis. The linear dimer will readily cyclize, and you get the cyclic dimer here. There's a little bit of debate about what the role of this is in this schematic, but suffice it to say that generally researchers will consider the cyclic dimer to be a problem for prebiotic synthesis of long-chain polypeptides. In like a Miller-type experiment, you see typical ratios of the cyclic dimer to the linear dimer, somewhere between 10:1 to 20:1. Okay, so we wanted to then measure the hydrolysis of this cyclic dimer, basically doing the same experiment again. So we did that, and remarkably, we found the exact opposite trend of what we saw before. So in this case, all the possible combinations of glycine and alanine, all three of them, and in each case, they hydrolyze faster in the presence of potassium than in the presence of sodium. And this, I mean, admittedly, when I first did this experiment, I was like kind of upset that, you know, it didn't go right, but then it's actually pretty interesting for a number of reasons. So if we look over here, this is basically, we're just comparing the rates of sodium and potassium. So anything that goes up hydrolyzes faster in sodium. Anything that goes down hydrolyzes faster in potassium. So this is kind of a cartoon model of the reaction scheme I just showed you. But if we're in a potassium-rich environment, then relative to a sodium-rich environment, you're going to have a higher proportion of the linear dimer, which then can go on to react to form longer chain polypeptides. And so these results kind of raise the possibility, I'll emphasize possibility, that life may have needed potassium-rich environments to optimize these kinetics, because although admittedly there are modest changes in kinetics, you know, given millions of years, a small change could kind of be what's needed to tip the kinetic scales, let's say. So also, I call it the flip, so the flip in the relative rates. It's useful for a number of reasons. One, it rules out the effect of cations on the structure and reactivity of water. This was our initial hypothesis, that there would be some difference, like for example, the activity of water of a sodium chloride solution is different than a potassium chloride solution, and that's pretty reasonable. We would think that would impact the rate of hydrolysis, since the rate determining step of hydrolysis involves attack of water. So if you lower the activity of water, you should lower the rate of hydrolysis. But if that were simply the only effect in play, then that would be the case across the board, regardless of which substrate you're looking at. It also rules out any sort of systematic errors from reagents or our methods. If we're weighing out we have a lot of water in our potassium chloride, and so we're not actually putting as much potassium chloride in there as we think we are, then that would, again, present itself as the same change across all substrates. What it does do is necessitate a direct role between the ions and the substrates themselves in the mechanism, which, you know, beyond the origin, the application to the origin of life, I think this is a super interesting observation, because if you ask an organic chemist to draw the mechanism for peptide hydrolysis, even in a sodium chloride solution, I don't think anyone would enlist the ions in that mechanism. But these results suggest that we should. So the next step for us is, how can we probe that interaction? We've done some work to try to do that, but so far all of our studies have been inconclusive there, so I won't talk more about that. But if you have any ideas about this, I'd be happy to hear them. So lastly, not to be outdone by everybody who has these amazing field sites all over the world, this is a picture of the Mississippi River that I took from just outside my lab. It's a really nice place. So lastly, I'd just like to acknowledge my group. Specifically, Annie and Mark are two really awesome undergrads, surprisingly great undergrads. Rio and Matt are the other two grad students in the lab. They work on some other stuff. And then funding sources. So yeah, with that, I'll take questions.
Thank you. Hi. For your rate of cyclization versus the rate of hydrolysis, are they competitive, or I couldn't see?
So we don't measure the rate of cyclization. That's been done. I can't recall the exact rate. I mean, when we have 1 molar HCl, it's not cyclizing. You know, it's only hydrolyzing for the most part. Does that answer your question?
Yeah, and my other question is, see if like it was a kinetic rate. You know, if you have a equilibrium where like the hydrolysis is faster than the cyclization, what about do you know the rate of going from your linear chain to the polypeptides? Or
I don't know that. Again, in acid, that's not really happening. You're not condensing at all. You know, there's a lot of work on peptide condensation in general. And that's where we're going to go next, is looking at that in the presence of sodium and potassium. Does that answer your question?
Yeah, I just kind of see if there was like a competition.
Yeah. There is in more mild conditions, but you know, we're trying to drive it that direction so that we can measure that specifically.
All right, that appears to be it.
All right.
Graham, are you saying a few words?